Okay, and I'm going to turn my video off so that it saves bandwidth. Okay, great. So welcome back, everybody, from lunch or whatever meal your time zone accommodates at this time. And we are about to go forward with Lisa Everett's second lecture on quark and lepton flavor physics. So Lisa, please go ahead.
All right, thank you very much. Thanks everybody for coming back, and let's see how it can go today. Hopefully a little more smoothly than last time, or at least a different set of interesting Zoom mistakes than the previous time. And again, Heather, etc., please feel free if there's questions on the chat. It's hard for me to see it and sort of write at the same time. So please feel free to interrupt when there are questions. I'm happy to be interrupted at any point.
Okay, I'll keep an eye on the chat.
Thank you very much. So last time, I just want to give a little bit of a remembering where we were last time. So we were still talking about sort of a standard model quark and lepton flavor overview, and we're continuing that today. But let me just kind of remind us. Basically, we talked about the fact that we have gauge eigenstates, right, that have simple interactions with the gauge bosons. So for example, that weak charge current, and like the following, G over root 2, sum over I, and then we had things like E bar Li. And now I'm going to put the zeros for the gauge eigenstate basis before I become lazy and stop doing things like that. And then we have the leptons as well. And then this one will be with W mu minus. And then we're going to have the same sort of thing for the W plus. Like so. And as we talked about last time, we have generally mass matrices for the fermions F, which would be U, D, and E. These are based on the Ucal couplings to the Higgs, which is in the standard model, only one Higgs doublet. So we can write down those mass matrices. And generically, they're not going to be diagonal on the same basis where these charge current is simple. In particular, we saw we can write down a biunitary transformation, UFL for rotation of left-handed fields, fermion mass matrix UFR, and that's going to be equal to MF diagonal. Okay, so therefore, the mass eigenstates are given by UFL dagger by FL, oops, there we go, 0. So what we can do, of course, is rewrite then the charge current in terms of mass eigenstates, and let me just do it for the quarks. We have G over root 2, and then we can now rotate to the mass eigenstates D bar Li, gamma mu, U dagger CKM J, and then this is ULJ, and this is W, this is W minus, CKM IJ, DLJ, W plus, okay, plus then there's the lepton part, okay, and recall the CKM, the Bibo-Kobayashi-Maskawa matrix, in our notation here is equal to U left dagger, U D left. So it's the overlap, as we can see from this form. And in fact, this is the thing that later on we've just been calling V. That's the standard notation for this very, very important matrix. Recall for the leptons, we're still in the strict massless neutrino sort of strict definition of the standard model, in which case we can always choose our degenerate masses for the neutrinos to be such that we can line them up with the E mu tau, and we can have basically no effects of any mixing in the charge current. Okay. And as we saw also last time, and we know, for the neutral currents, In other words, photon Z Higgs. These are all flavor preserving. They're flavor preserving in the standard model, and that's very important. So in other words, when we write them, they have a certain symbol form in the gauge eigenstate basis, and then the electromagnetic and weak neutral current are having a very simple form also, a flavor diagonal form in the mass eigenstate basis.
Hey, Lisa, there's a question.
Yes.
How many physical parameters would the CKM matrix have if two of the up quark masses were degenerate?
Oh, yes, I think I saw some of that question being discussed. And indeed, that's an interesting question, because when you have degeneracy, then of course you can, in a 2x2 subblock, you can have the freedom to make a full unitary transformation, including a rotation angle as well as 3 phases. So I believe the parameter counting discussed in the Slack discussion, which I sort of took a peek at one point, is in fact correct. And I believe the interpretation there is that if you, when you have a degenerate pair of ups, for example, we then have 3 downs that are not degenerate. So we have to sort of talk about the interaction of sort of these up set of things with the 3 different downs. And so I believe you can basically choose such that one of them is a simple coupling between the up and the down, and then there's going to be some kind of mixing angle between that pair and the second down, and then another mixing angle between that pair and the third angle. So I believe it's 2 parameters. And no CP violation, because we know that the only way we can get that is if we basically have so 3 full families to be able to have the phase come in. Okay? So I believe that's the correct counting, and I'm happy to sort of take that up in further detail tomorrow, for example, at a discussion section, etc.
Thanks.
Okay, so let's go on to talk about the masses of the quarks and the charged leptons. And as I talked about last time, I wrote down all their their values as of current understanding at the Pdg review level. And what we see is that we have strong hierarchies. So in particular, if you plotted the masses, and let me try to draw things, this is always, I'm not one of those people blessed with artistic talent, so please bear with me while I make an attempt. So let's draw some sort of log scale. Right? So we can look, for example, the charged leptons, we would have the E, and then we have the mu, which is probably around here somewhere, and then we have the tau, like so, sort of equally spaced, roughly speaking. And then we're going to have for the up-type quarks, we have this here, up-type, and then charm is over here. Top, as we know, is quite large, close to the TV. The T doesn't look like it. And then finally, there's going to be the D. The S is pretty close to it, comparatively speaking. And then the B is around here somewhere. Actually, B is bigger than C, so let me try to draw that so that it makes some sense. Oops. All right. All right. So the point is, it's very strongly hierarchical. I didn't write the neutrino masses. Of course, we don't exactly know where they are, but wherever they are, they're going to be down here somewhere, right? Because we know something about limits on their absolute scale, as I'm sure Andres talked about. Okay, so we have these strong hierarchies in the quark sector and the charged leptons, and it's very striking. And then furthermore, we talked about the quark mixing. I'm going to make this a little bit bigger, I think. Okay, let me scroll up a tiny bit. Okay. All right, this is our friend, the CKM matrix V. Okay, so here, let's just write it all out again. Okay, like so. And I talked last time about the Pdg parameterization There's 4 parameters in there. There's 3 mixing angles and a phase. It's traditional to order them this way, sort of Euler angle decomposition, where we put the phase angle in the 1,3 mixing part, which is sandwiched in the middle. And then finally we have the 1, 2. So that's the look of it. There's the 4 parameters. We know that the mixing angles are such that sine theta 1, 2 is much bigger than sine theta 2, 3, is much bigger than sine theta 1, 3. But all of them are actually pretty small. Okay. So in other words, the theta 1, 2 is the largest one, and it's close to the sort of 2-family Cabibbo angle, which is basically of order 0.2. And we'll talk a little bit more about the details as we did sort of last time as well. So we have essentially that quark mixing is almost the identity, but it has tiny off-diagonal elements. The biggest ones of those small elements are in the 1, 2 sector, and then the 2, 3, and then the 1, 3. So we have sort of these hierarchical ways in which the mixings come in. And that fact was exploited by Wolfenstein in the Wolfenstein Parametrization, which is, I believe, pretty close to where we left off last time. So the idea here is we can write V as a power series in the small parameter lambda, which is approximately sine theta 1, 2. That's rho minus I eta. This is 1 minus lambda squared over 2 minus lambda, a lambda squared minus a lambda squared, 1. I can't draw a matrix with my pen. Okay, there we go. Now we have a lambda cubed, 1 minus rho minus I eta on this side. Okay. And this is to order lambda to the 4th, to order lambda cubed, so there's order lambda to the 4th corrections. Remember, lambda is basically approximately equal to sine theta 1, 2. And then the other 3 parameters are a, rho, and eta. Because we have to go to higher order at this point, given the precision way we're measuring up the CKM to the data, we also define the quantities rho bar, which is rho 1 minus lambda squared over 2. And we have eta bar, which is eta 1 minus lambda squared over 2. Okay, and those are going to be important quantities for us. So we have these 4 parameters, lambda, a, rho, and eta, or equivalently, we can describe CKM in terms of the 3 mixing angles in the 1 phase. The invariant measure of CP violation we talked about last time is the Yarlskog invariant. Here's one way to define the thing. Imaginary part VUS, VCB, VUB star, VCS star, and that's equal to cos 1, 2, cos 2, 3, cos 1, 3 squared. Try this again. That's better. Sine 1, 2, sine 2, 3, sine 1, 3, sine delta. Delta being the CKM phase in the Pdg parameterization. And in the Wolfenstein, this thing is basically of order a squared lambda to the 6th eta. So small. It's a very small quantity if you actually put in the values. It's small in the standard model, not because the phase parameter itself is small. It's not. It's basically an order 1 phase angle, but it's small in standard model because of the small quark mixing angles. Okay. Now, let me just make one comment before I go on to sort of new things. Another question that came up yesterday that I said I would look into, and I did a little bit, was the question about the VUS element and whether there was a difference or a strain between direct measurements of VUS, which are going to come from some various kaon type of decays, or from the unitarity constraints, because then if you measure the other quantities, you should be able to get it from unitarity. Okay. And the answer is that if you look at sort of any kind of recent discussions of these things, basically, it seems like the issue, which used to be there, was resolved. It used to be that the direct measurement of VUS was actually too small somehow, and it was making one wonder. Unitarity seemed a little bit off by, I think, maybe at most a couple of sigma. And apparently what happened was there were higher precision direct measurements of the VUS, which when those were made and interpreted, the VUS value went up. So that's now at the level of, I think, looking at this issue from before, a long-standing issue apparently was actually resolved. Okay. But the main point is one really wants to experimentally get a handle on all of these entries of CKM matrix directly so that you don't have to infer anything from unitarity, because that's probably what you're trying to test in the standard model. This should be a unitary matrix, and therefore it should satisfy various constraints. Yes. Is there a question?
No, I think we're good.
Okay, good. I couldn't quite tell. Okay, so now let's go back to the unitarity triangle. Okay. So if you remember, one of the unitarity tests that turns out to be particularly useful and interesting experimentally is the following combination: VUD, VUB star, plus BCD, BCD star, plus VTD, VTB star. And the reason why, and this thing all stay equal to 0 because of unitarity, okay, at least that's the test. And so the reason why this particular combination, there's many other such combinations, from taking V dagger V and making, or VV dagger and making sure all the off-diagonal elements are 0. But this one's the most interesting because the different contributions are also similar in size. So what you have is a rather open-looking triangle if you draw these things as a triangle in the complex plane. So I believe where I ended up last time was to talk about this triangle, terrible looking triangle, but you get the basic gist of it, hopefully. And so this length would be VTD, VTB star, divided by VCD, VCD star. So we're going to normalize it by that second one. This one is, oops, come on, everybody, let's not do that. This one is VUD, VUB star, over VCD, VCD star, and this one is 1. And then the three angles here on my tiny little picture. This is angle beta, this one is angle gamma, and that one's angle alpha. Okay. And alpha, beta, gamma are all quantities that in particular could be inferred from CP violating observables. In the standard model, these are all due to the one source of CP violation, which is the CKM face delta, as written in the standard parameterization, or equivalently the eta parameter or eta bar, okay, as written in the Wolfenstein. Okay. And so the idea was to establish these quantities experimentally, and this is where the B factories became very much importance. And in particular, as we'll see, and one of the things we'll discuss today is that in particular the angle beta, which is going to tell us something basically about the TD entry of the CKM in particular, this quantity turns out to be related rather simply to a particular decay of the BD meson to J psi K short. And this one was called the golden mode because it happens to be relatively free of hadronic uncertainties, which plague some of the extraction of these other parameters. But we want to basically get this thing to work out. And so if we rewrite this thing in the Wolfenstein parameterization as so, I'll try to draw it a little bit more nicely. I really don't like how this thing looks. Okay, so then if I plot this thing in the rho eta plane, if you like, okay, let me call this 0, 0 in rho bar eta bar. This would be 1, 0. And then this point up here would be a rho bar eta bar point. Okay, and so this is basically the same sort of thing when we put in our expressions here. Go to the next page and scroll back up. In particular, we see we can write VUD, VUB star over VCD, VCB star. Absolute value is just basically then equal to square root rho bar squared plus eta bar squared. Okay. So this is a particular constraint then on this triangle, and if I was doing slides or giving a talk or whatever, I would pick the beautiful figures that there's groups called, there's two groups, CKM fitter and UT fit, I'll talk more about later, we're looking at all the data and trying to constrain in the rho bar eta bar plane this unitary triangle and to see where we are in terms of pinning down the parameters. Let me try to show you the type of the way the plot sort of looks. I don't like that either. Okay, let's see if I can do this. Okay, so here's rho bar, eta bar. Okay, and I'm going to draw my triangle, sort of like this. Okay, you get the basic idea. This is the beta. This is beta, this is gamma. This is alpha. Okay, this is my rho bar, eta bar point. And we can see right here, this constraint is another thing. It's a circular constraint. And this thing goes by the name of the VUB constraint. Okay, and if I can draw this, we can see this is going to be a circle. It's a circular constraint, so we're going to get something like this. Right, like so. So basically VUB would need to, if we're having a consistent picture, to determine VUB, it should lie within this sort of semicircular part. And as you can imagine, the more data you have, the more you try to pin down where this thing should go. Okay. And the idea ultimately is to test this Kobayashi-Markskawa picture of CP violation. Some actual website or something like that? Okay. Because I'm hearing something.
Andre, I think you're still unmuted. Thank you.
Okay. Okay. So what I hope to discuss today is to give a little bit of a sense of how we test experimentally this picture of quark and lepton flavor mixing and CP violation in the quark sector of the standard model, remembering that this is a very specific structure that we have. So in particular, let's just remind ourselves. So let's just step back a little bit. So flavor structure in the standard model. We've seen it's very specific. Okay. So we have flavor violation in the charged current only. W exchange is the only way we can change flavor in the standard model. Okay. That's important. And then furthermore, the small angles of the CKM generally mean that there's going to be preferential decay processes. So for example, we're going to have a typical chain where you first go from T to B to C and then to S. Okay, so for example, if we start with a B, then we can go to the C dominantly via the tree. We can also go to U via a tree, but this is CKM suppressed compared to the closer one. This is because of the fact that essentially the generations flavor mixing in the standard model empirically is such that, right, essentially the matrix is almost diagonal and they connect the nearest neighbors the closest. Okay. Now, also we know that the neutral current the standard model is tree level is flavor preserving, which means if we're going to get neutral current processes that change flavor, they're going to have to come through loops in the standard model, through loops involving the W's. Okay. So for example, if we want to go from B to S, from a bottom quark to an S quark, that's not allowed to happen at tree level, but we can get it through loops. Okay. And so these go by the name generally of these flavor changing neutral current, which we label as FCNC, and that's just a very common abbreviation. Okay, and so these are rare decays, and if you get a sort of a sense of it, if you compare basically tree amplitudes, they can be sizable parts of their branching fractions can be sizable for the decays of any particular hadron. But for the ones where you're talking about a rare flavor neutral current event, like a B to S transition, these are much, much smaller, so orders of magnitude smaller. They're known experimentally to be suppressed basically of order the G Fermi squared, okay? And we'll see later is that there's a further suppression mechanism that can be active. I don't know what that is, but I don't like it. Okay, further suppression mechanism that can be active is what's called the GIM suppression. And that's the Glashow, Iliopoulos, Miami. And that's, that was name right? No, I did not. Let me do better. That's better. Okay, and this is, I believe, 1970. And this was very important because in the development of the standard model, this was the idea, right? Because we know it's these left-handed fields that have that seem to experience the charge current interaction, the W, of course, and what it meant was that every one of them should be in a doublet representation, right? So we know this very well for the standard model, right? But prior to the development of it, it was basically, for a while, we knew the quarks perhaps up, down, and strange only. And so this idea that, for example, there should be a partner to the strange quark that goes by the name of charm, similarly the way that the up and down, kind of like isospin partners, okay? These were sort of extremely important developments, and they're needed. Otherwise, if you don't have that charm partner, what will happen is when you go and you calculate these flavor-changing rare events, they're much, much too large. So there's all kinds of suppressions that happen, and this GIM is the sort of first place in which one sort of really saw that. And in fact, those were extraordinary times, if you think about it, really for particle physics theory, if you like, because this was the time when one was predicting the existence of a new fundamental particle based on data, and then indeed it was actually found exactly where. and in fact, getting some sense in how the kaons mix, as I'll talk about a little bit later today, one can actually have a fantastic sort of calculation, estimation of that process that was done by Mary Kay Gaillard and Benjamin Lee back in 1970s, early 70s as well, where they actually predicted the mass of the charm quark, and it was discovered at right around that value, which is really amazing, okay? So let's go on to talk a little bit more about this GIM suppression, okay? So this connects here with this particular bullet point. So essentially, the point is the weak gauge coupling G. This is of order electromagnetic. Okay, it's a bigger, but it's around that same sort of order. And then the point is, experimentally, for a long time, it was known that the FCNC events are basically of order GF squared at most, where GF is the Fermi constant. But one could imagine without this type of suppression, maybe there could be effects that went something like order GF times alpha, a fine structure, and they're actually bigger, okay? And in fact, it was this GIM suppression idea, the main idea is that, again, the CKM is unitary, okay? That, and every quark has this sort of weak interaction partner in the left-handed sector, these doublet representations that were critically important to suppressing what would otherwise be huge new amplitudes. And that's an important lesson also for new physics. If you sort of arbitrarily put things in, then what can happen is generally you're going to spoil this very delicate property of the standard model, that we have these very strong suppressions of the neutral current flavor changing events. Okay. So let's go over this one a little bit more with respect to, say, let's take a B to S transition. So let me just draw some little diagram here. So here's a B, sorry everybody. Here's a B and an S. And Here's a W. You can see I have to work on my pen skills with this tablet. Let's see if I can improve over the course of this lecture. So here is, not going well so far. Here in the loop are the U, C, and T. Okay, so here's a usual B to S transition. It's loop induced, okay, in the standard model. And so our amplitude, we can see, is going to look like the following. So I'm going to write the amplitude A for this B to S. We have VUB at one vertex, VUS star. And then there's going to be some coefficient, okay, where I'm going to call it F tilde U, just because then that's the term with the F quark in there. Then we're also going to have the VCB, VCS star. And then there's the charm contribution. And finally, there's VTB, VTS star, and then there's the top. And again, these coefficients F tildes are basically functions, for example, of the quark masses mu squared or mc squared or mt squared over mw squared, etc., just from doing the loop integrals. Now, because of CKM unitarity, what we can do is we can take, for example, VCB, VCS star, and we can rewrite it as a linear combination of the other two with a minus sign out front because of the fact that this thing obeys the unitarity constraint. So we can write, for example, CKM unitarity tells us that my A, B to S is going to look like the following: VTB, VTS star, F tilde T minus F tilde C plus VUB, VUS star, F tilde U minus F tilde C. Or remember again, the F's are basically going to be some functions of M squared U, C, or T over MW squared. Okay. And basically the same function, just depends on which quark mass you have in the loop. So what we can see is that if all the quarks were degenerate in mass, then all the F tildes are equivalent, right? FC tilde is the same as FT tilde, which is the same as FU tilde, and that means that the amplitude will vanish. Okay. And so this is again because of the fact that we were able to express these things via the unitarity, and we get these constraints where it just depends on these differences of these functions. So the amplitude clearly is going to depend on the mass differences of the quarks in the loop. Okay. And in fact, what we can see is depending on what process you're dealing with, there are going to be various suppression factors that come in. So in this particular case for the B to S, we have two entries in here. We have VUB, VUS star, and we have VTB, VTS star. But VUB, VUS star is actually much smaller than VTB, VTS star. So let's just write that out. VUB, VUS star, and here let's use the Wolfenstein parameterization, just keep track of the lambda power. Remember, lambda is a order of 10th. Okay. And this one goes like lambda squared. So what we see from this is that here the top quark in the loop is dominating. That's kind of expected, right? This is a more important part of the process. So very often when we have these types of transitions, B to S, it's going to be the top term that's going to dominate. Okay. And well, let's see, what do I want to say next about this? Yes, for example, if instead we had, for example, a tree level charm to U transition, okay, then the types of factors we would have would be VCD star, VUD, and VCS star, VUS. And sometimes they can be very similar in structure, okay? And so if that's the case, then what can happen is you can still end up getting a very, you can get contributions, but they still kind of almost cancel each other, and you can get a very strong Jim suppression, okay? for C to U, basically, this is the external up-type quarks. So then the internal quarks are the down-type quarks. And the down-type quarks have a smaller mass splittings as well. So basically what we'll see is there the GIM suppression for C to U is going to be stronger than it is for the B to S, and that's important. But generically, these things go like GX squared delta MQ squared, where these are the quarks in the loop.
Lisa, there's a question.
Yes.
When we say that the off-diagonal elements should vanish, why do we only focus on the V squared BD? Is there another triangle that we need to check?
There are lots of triangles, and indeed in practice you would want to check lots of different ones. The main reason why people focused on the BD triangle in particular, well, there's a couple of reasons, but the primary one is because it's by far the most open one, meaning that the sides are relatively similar in length compared to some of the others. So some others, remember that these are talking about different combinations of the CKM entries, and they vary a lot, right? We have order 1 entries, and we also have an order lambda, and we also have lambda cubed. So depending on what gets multiplied with what, we can have triangles where you can have one extremely large side and two others that are very, very short. So they're very hard to see, you can imagine, right? So indeed, people have been looking at other triangles besides just BD, right? BD was the first one to sort of fixate on, and it also turned out experimentally to be of use and accessible because of the fact that, first of all, we see that the BD mesons can mix with each other, and one can have a very nice set of experiments, which are called the B factories, where we have E plus E minus goes to a Botonium resonance, a excited state, which is going to decay basically 50% of the time to BD bar, and you can tag. Okay, so we had both experimental and theoretical reasons for focusing on it, but people are now looking at, for example, triangles associated with B sub S, right, SB rather than BD, and one can, if you're really good ambitious, look at ones involving kaons. Okay? The issue is the more you get towards situations where you're dealing mainly with light quarks, then you start having to be even more concerned, and it's already a big concern with hadronic uncertainties, perhaps blocking you from being able to extract these sort of underlying standard model particle properties that we're looking for from the data.
There's another question. The processes as you drew them aren't literally possible, right? You need, e.g., a photon emission as well?
Yeah, these are just going to be part of some bigger structures.
Mm-hmm.
Yeah, this is just one sort of, piece of some bigger diagram representing some other process. Yes.
Another thing you can have is like one meson decaying into two mesons.
That's right.
For example.
Okay, so let's, are there any other questions out there, or should I go on?
Sorry, I had to unmute. That's it for now, right? So
No,
yeah, please go ahead.
So here the thing to keep in mind is there's going to be larger effects generally for external D quarks, D-type quarks, I should say, than external up-type quarks. The simple reason that we know that the up-type quarks are much more split, okay, and in particular the top one being so much far further away from everybody else gives a chance for it to come in and be relevant and important. Okay. Now, what about the leptons? I'm just going to sort of say this in words rather than writing it all down. Remember, from the lepton point of view, essentially any experiment that's not sensitive specifically to neutrino masses is going to give you the situation where the lepton flavor is essentially unobservable in the standard model. So any sort of lepton flavor violation, if it's observed, it would be essentially telling you that there must be physics beyond the standard model in these types of experiments. Okay. And not just physics that gives rise to neutrino masses, but something where those degrees of freedom can be operating and important at these energies. So ultimately, the point is that the standard model has a very, very delicate structure. we see that there's these sort of three mechanisms really for the suppression. First of all, the neutral currents. First of all, they can't happen at tree level. They can only happen through loops. Second of all, we've seen that empirically the Quark mixing, which is governing the strengths of those things, is essentially flavored diagonal up to small corrections, order Cabebo angle lambda, and powers of it. So it's very small. And finally, we also have this Jim suppression showing us, because we have these objects really in SU2 left doublets, that's providing us this means to understand their weak interactions. What we can have is generally the amplitudes would vanish if we had degenerate quarks in the loop, and so therefore they're proportional to splittings. So we have three mechanisms for suppression. Generally, new physics that you come in to write down is going to essentially, it could obliterate many of those things, okay? We know that it's going to be very, well, let me put it this way. As we'll see later in dealing with some of the B physics potential anomalies, which are at the level of a few sigma but have been persisting for a while, there has been proposals to introduce new tree level flavor violation by introducing exotic particles like Z primes or lepton quarks, which could do that. Or you can also have new physics that, you know, provides new sources of neutral currents at the loop level. And supersymmetry is one of the many examples of theories that are generally going to do that. And when they have that, they're not at all going to necessarily have the same sort of structure of flavor mixing among those that's predicted, and you're not necessarily going to have this Jim cancellation continuing to be operational with these new features. So this provides extraordinarily strong constraints, as we'll see, on possible new physics models or new physics that can come in at a TeV. And this goes by the name of the new physics flavor puzzle. So tests of these at picture then is extremely important, and they've been ongoing for decades now. And the idea is really to just look at all the places where we have flavor violating processes, especially via neutral currents in the standard model, test the unitarity triangle, test the CKM entries, right? Test the unitarity as much as we can, and see, and we want to over constrain, because as we know, there's only a few parameters in the CKM matrix that are going to give us these things. So what I'm going to turn to now is basically a very brief overview of sort of the developments and the current experimental situation. Okay? And it's brief because I just want to right now give a disclaimer that this is an extraordinarily important topic with an enormous amount of work and done by expert practitioners in standard model physics and the hadronic physics needed to deal with the hadronic matrix elements, because ultimately for the quarks, the objects that we're really dealing with are going to be hadrons, and we have to understand the non-perturbative QCD effects, which are of critical importance, absolutely critical, and that's where a lot of the theoretical uncertainties lie, but it's also where an enormous amount of progress also has been made. And of course, there's expert experimentalists who are coming in to measure all these quantities. So this is just a disclaimer to say I'm not a practitioner of this area, but I'm hoping to provide you a little bit of a kind of, maybe cartoon version. It's basically a little bit of a guide, and I'll try to give you some references, or if you want to do further reading, there are experts to follow. Okay, so let me just first talk a little bit about, in particular, one of the main focuses is going to be about CP violation, right? This is related to our friend the unitarity triangle, that alpha, beta, gamma angles are all there because there's a CP violating phase, okay? And so there's two types of CP violation, if you like, that
Actually, Lisa, sorry, can I interrupt for a sec? There's another question which I think is related to the how you say, the neutral current transitions.
yes.
And is the effect for D type larger than for up quark because of 3 to 2 transition compared to 2 to 1 transition? Or in other words, is S to D also Jim suppressed?
S to D is Jim suppressed, certainly, yes. S to D is actually a little bit more complicated because they're essentially, let me put it this way, the B to S, we sort of see the dominance of the top quark piece, as I just showed you in this expression for that combination of entries that comes in. For the D to S, both the charm and the top are actually important, and they both need to be there, absolutely.
Okay. What about like charm to up?
Yeah, charm to up is the situation where I would say the Jim suppression there is generally stronger. right? So I think I sort of started that. Let me maybe, you know, sort of imagine if we go back to the same kind of argument that we had, let's scroll up a little bit, back up here when we talked about the B to S and wrote it in terms of amplitudes. For example, a C to U, you would have something like the following: VCD star VUD, and then you'd have, for example, an FD tilde minus FB tilde plus BCS star BUS S minus FB, okay? And if you put these things in, then what you see is this one's basically of order lambda, and this one is basically also of order lambda, and they have opposite signs, and so I think this one's the minus lambda. Okay, so we can see is that if, again, these amplitude, if these functions, the F tilde is in there, if they're very similar to each other, then there's going to be a very strong cancellation. Whereas in the B to S, right, in the B to S, what we see is that the first term really in this expression for A, B to S that I have here, it's dominating because it's much less CKM suppressed than the second term. That means that the C to U is going to be very, very sensitive to new physics effects, because if the standard model is wanting to cancel itself out to oblivion, then what will happen is if there's new physics creeping in, it can make itself seen more easily than in some of the other sectors. Okay, so let me go back to, we're talking about tests now of this picture, and CP violation, there's basically two different sort of general categories that I'd like to describe here. And they go by the names of indirect and direct. Not very poetic, but that's what it is. Indirect is the idea that it occurs through mixing. So for example, you can have neutral mesons that then mix, KK bar being sort of the archetypal example, okay? And you can get CP violation occurring through mixing, or you can get it directly, for example, in the decay, when the mesons, for example, decay to different particles. And so one of the things when trying to test the CKM picture for mixing and CP violation was to sort of determine, do we see both indirect and direct effects? And it turns out we have measured both of these things. The indirect via mixing essentially is again first seen basically in the kaon sector, and that's in a small mass difference between the K and K bar neutral mesons, as I'll talk about in a little bit. Furthermore, CP violation entering through there's a parameter called epsilon, and that parameter is associated mainly with indirect mixing-induced CP violation. But we also have in the kaon sector a direct contribution, which goes by the name of epsilon prime. And so the epsilon, which is primarily mixing, and I'll write it as epsilon sub k for kaon sectors, observed to be very small, order 10 to minus 3. And then epsilon prime over epsilon, and now these both should have a k on them, again for kaons. This is also very small, order 10 to minus 3, so we can see epsilon prime is even smaller. And these were all measured in the context of looking at decays of kaons to pions. And this was the first sort of historic observation of CP violation in the weak interactions by Cronin, Fitch et al., who were looking at kaons and saw that something that shouldn't be allowed if CP was a good symmetry was in fact allowed at a suppressed level, and that's related to the fact that CP is violated in the characteristic small size of it, order 10 to minus 3. And that's a big part due to actually small CKM angle suppressions that show up in this process, okay? So generally mixing, when we talk about mixing, if you like, let's talk about those processes as basically delta F, where F would be the flavor, equals 2. Okay, so maybe there's the flavor sort of content changes by 2 units. So kaons are S D bar and D bar S are the neutral kaons, and so this would be to go from one to the other, you have to sort of jump flavor number by 2. And similarly for the B mesons, the BD and etc. And finally, the decay would be a situation more like the types of things I talked about above, where we change flavor unit by 1. So for example, with a B to S or B to something like that. Okay, just one time rather than both. So these are the things people have been studying and looking at. And what I'd like to talk about very, very briefly, because I think it's useful to sort of see it, is let's talk about the kaon system. Okay, and again, this is sort of in the broad brush stroke. Okay, so here are these two particles, the neutral K mesons, and you can see these are what we call strangeness preserving. So they have a particular quantum number with respect to the S, right? So the K, for example, has an S bar and the K bar has an S, right? And strong interactions turn out to preserve this S. As we know, these things don't change the flavor, but the weak interactions, as we know, they do. And so what can happen is these particles can mix. So we can write down, roughly speaking, a 2 by 2 mass matrix for their mixing. And I'm going to write this as M, K, K, K bar. And the important thing to notice is that this here is some tiny effect due to the weak interaction mixing, because you can exchange W's at a loop. I'll draw the diagram in a minute. So you might think, well, that's not going to be that important, but notice the diagonal entries of this matrix are equivalent. They're equivalent because of CPT. Okay, they're equal by CPT, and that means that even though the perturbation, the off-diagonal part, is very tiny, it has a big effect, because as we know, perturbing degenerate structures can give you a maximal type of mixing. Now, historically, this was done sort of thinking only about 2 generations and not all 3. So if you ignore the third family, which I'll do for the moment, okay, then it turns out this off-diagonal mixing MKK bar is real. Remember, if we don't have 3 families, we don't have CP violation that's observable. If we only have 2, we can rotate that phase away and it's unobservable. So we only get real, okay? And then what will happen is the eigenstates in this case would be what we call K1, 2, not, and these are just the maximally mixed combinations. Okay? And these are CP eigenstates. These are -1, okay? Now, if we include the third family, then there's small effects again, but there are imaginary pieces in the MKK bar. So what happens is that if we have the third family, these K1, 2 are not quite the eigenstates. So the CP eigenstates are not quite the eigenstates. Instead, what we have are the eigenstates, what are called K short and K long, okay? And they're called K short and K long. They're approximately equal to K1 and K2, okay? But not quite. They're not quite the same. There's a tiny admixture of the other components. So K short is approximately K1 naught, but it has a tiny admixing of K2 naught with a phase. And similarly with vice versa with the other one. And the reason why they're called short and long is because it turns out that the K short is always going to decay to 2 pions, okay? Because of CP quantum numbers, it's allowed to do that. But the K long, that's forbidden, the 2 pion decay. It has to decay by 3 pions. So therefore what happens is that the K short has a much greater phase space for decay, and so it's going to decay much faster. So it has a much shorter lifetime, whereas the K long, is much longer. And that turns out to be extraordinarily useful experimentally, because it provides a way to sort of separate out the 2 contributions. This is a feature that will not be generally preserved for the B system, because there's going to be many decay channels for example, the BD and the BD bar. So you're not going to have this sort of one's a short and one's a long in the same way we do in the kaons. Okay. But the main point was that the famous first observation of CP violation was this idea that the K long could decay also to 2 pions. That would only happen if we have CP violation, because normally it would only be allowed to decay to 3 pions, and that's precisely the Cronin-Fitch Nobel Prize winning discovery from the 1960s. Okay, so what we can do is we can talk about how you would actually try to model this process. Let me just draw a box diagram. So here we have it. So here is D and S, S and D. Okay, here's W's. And then these here inside are U, C, and T. Okay, and here let's just draw the arrows. Okay, like so. Okay, so you can see on this side, if you like, this is a K bar on the left-hand side, and on the right-hand side, it's a K. So this is an example of a delta F equals 2. Here I'm writing F, the flavor number is related to the strangeness, so this is delta S equals to 2. There's other, there's another box diagram where instead of having it with this topology, it's slightly different, but it's the same basic idea. And so what you can do is calculate these graphs, and we can write down, therefore, an effective Hamiltonian. Okay, and this thing squiggles like the following, GF squared. And then I'm going to sum over I, the quarks in the loop, VID, VIS star. And then we also have a sum over J, VJD, VJS star. That out. And then there's going to be sort of loop functions, Fij, that are going to depend on the quarks I and J in there. And then there's essentially an effective operator. So imagine what we're doing is we're sort of integrating out the W, if you will. Okay. And I'm going to get the following sort of operator structure. D bar L gamma mu SL, D bar L gamma mu SL. As we can see, it's the same structure on both sides, okay? And so this is the type of thing that we have, and we can basically then calculate, for example, this thing that I was calling MKK bar is squiggle. I'm being extremely sloppy, basically about all factors. This is why I said this is really a cartoon version. Right, you'd have to then understand this in the context of taking the hadronic matrix elements, and then the delta MK, so the differences between the mass eigenstates, masses K of K short and K long, delta MK, that this thing is basically goes like this MKK bar entry in this 2x2 matrix. Okay. And this is the place where it turns out when you do the calculation, the charm is dominating. In fact, as I said, historically, this was first done in the context of ignoring the third family, and that's the Gaillard and Lee sort of showing that we're going to get contributions to the delta MK that are going to go like VCD, VCS star quantity squared, okay? And that's actually extremely important. That's this tiny splitting, and it's also going to depend on M charm squared. In practice and reality now, one, as I said, has to include also the tops and et cetera. It's much more complicated. You also have to include QCD evolution, okay? Because one's often trying to go down to the sort of the mass scales of interest, more like the kaon type mass scales, et cetera. So there's QCD corrections, all kinds of important work to get this thing to the level of precision. Not to mention, there's the issue of you need to evaluate the hadronic matrix element, which, as we can see, doing this sandwich here is going to basically be affecting how you put in these operators. And so there's a sort of quick and dirty way to estimate this, which is called vacuum saturation, which is not expected to be a good approximation, but that's just sort of inserting the vacuum state between the DNS operators wherever you possibly can. And then you can relate this to other things that you can measure, and you can get an expression for the delta MK, which goes like the following. It goes like GF squared and the charm squared. And then we also have an MK. There's various hadronic related coefficients, and then we have the BCD, BCS, BCS squared, okay, for this object. So now when you look at these kinds of things, you can then imagine here's a situation where maybe you set up an experiment that you start off with a K0 at time t equals to 0. So roughly speaking, that's basically an equally weighted linear combination of the short and the long. And then because the short and the long have different masses, they're going to evolve differently in time. And then what you can do is you can measure then the delta MK through sort of regenerating the K bar piece, for example, after certain time allotment. And of course, in practice, you have to be a lot more careful. There's not just the mixing happening here, there's also decays. So when I went up here and I wrote this mass matrix, what I really should also include is another contribution, effectively, that's imaginary part, that's representing the fact that these states are also going to decay with themselves. Okay, so I'll talk about that momentarily when we sort of generalize this arbitrarily for meson mixing. But let me just make a comment that here's our delta F equals to 2 process. And then what people can look at, for example, are things like the following. You can look at the amplitude, right? The amplitude for k long goes to pi pi, over the amplitude for k short goes to pi pi. And you can either do the plus minus combination or the 0, 0. And those are going to give you either eta plus minus or eta 0, 0, depending on the pion state. And these are the places in which one extracts. These are a squiggle equal rather than a real equal. Epsilon plus epsilon prime, those quantities I was telling you about before. This one's epsilon minus 2 epsilon prime. Okay. And basically it's from these that one has to, as I said, one has to really deeply worry about the hadronic uncertainties, et cetera, and all of this, but this is where one extracts from data these epsilon and epsilon prime over epsilon to be these small numbers that I told you about before.
Okay, so one comment in
yeah.
your effective Hamiltonian,
Yeah.
one of those, the comment is just that one of those D bar S's should be an S bar D.
No, it should not be. If you look at the structure,
Oh, really?
Yeah, look at it. The structure is the same. S goes in. All right, if you follow the arrow, it's the same.
Oh no, you're right. Oh my gosh, 2 S's go in, 2 D's
yes,
come out.
It seems weird, but
Awesome.
it's
Okay.
because the delta S equals to 2 part. Yeah, that's right.
One's the initial state, one's the final state.
That's right. That's right. Okay, so the main issue is that kaons are really exciting, and this even sort of dates back to my long ago days as a grad student and early postdoc myself. In the late 90s, et cetera, and even late 80s, basically, we sort of kaons and people working, but then the problem is because the K's involve the D and the S, and these are light, there's a lot of uncertainties, and it's a tricky business generally. And then in 1987, there was actually observation of similar mixing of the BD meson with BD bar. So BD is DB bar, and BD bar is D bar B. Okay, and so that was actually exciting for people because not only is there this idea that we can then understand probing, perhaps with it, we can see the CP violation via the mixing in that process, but also because of the fact that, if you remember, it's this BD unitary triangle that we talked about earlier, that's the one that seems open and maybe a possibility. So the main thing is to sort of have an experimental handle on it, and so seeing that was sort of what gave people the idea is to pursue these B factory experiments, which were operational from basically the very late 90s through most of the early 2000s. And now those are Babar and Bell. And currently we have the Lhcb experiment, of course, a collider environment, quite different, but it has its own great sets of advantages, and also the next generation B factory, which is Bell 2. And so the idea was then to sort of probe these BD system, and you can also at Lhcb probe the B sub S system. So instead of D quark with B, you have S quark with B, and measure mixing, et cetera, there. Okay. And so the reason why this is actually exciting experimentally also is you think about the semi-leptonic decays, for example, of these mesons, right? Since, for example, the BD involves a B bar, right? You can then look and you can say, okay, suppose I have a B bar to C bar transition through a W, and then I'm going to get that W is going to go to an L plus and a nu, so a neutrino, whereas if I had the B bar, that has a B quark in it, and so that's going to go B to C, and I'm going to get an L minus and an anti-neutrino. And so what you can do experimentally is you can look to see, for example, you expect the positive lepton, right, the anti-lepton or whatever for the B decay, and you expect the opposite charge one for the B bar. And so in fact, it was seeing the fact that you expect opposite sign leptons if you produce a BD bar pair, and it was actually seeing the same sign leptons in some processes. It shows us first that there was actually BD bar mixing. So let me just, in the last few minutes today, give a little bit of a introduction, a tiny bit, to the idea of the B factories. So these are the BD system. And the idea would be to take an E plus E minus collider and then sit on a particular BB bar resonance. So this goes by the name of upsilon 4s. Okay, it's one of the excited states. And the reason why this one's exciting is because 50% of the time it decays into a BD 0 and a BD bar. By the way, the other 50% of the time it decays into a BD plus, BD minus pair. Okay, so this is a factory, so we can sit right on the resonance. We can produce huge numbers of these. Basically, have a high intensity source of this object and study the system in quite some detail, which they did over the span of more than a decade. And one thing experimentally that's useful to know is that these are what are known as asymmetric, meaning we're not colliding them with the same energies. We wanted to give this upsilon object a boost in the lab frame, and the idea is then you can perform a better separation between the decays of the BD and the BD bar. And the reason is because both BD and BD bar have very short lifetimes, so you need to be able to sort of separate them. That wasn't an issue in the kaon system because we had a K long and a K short, and they kind of did that for us sort of naturally. Okay, so here's the excitement then about what these types of things can see. So imagine we talk about a BD particle, and here whenever I write BD, I mean BD naught, okay? Suppose it can decay to some final state F. So the final state could be pions, it could be J psi, K short, it could be various objects, okay? So that's path one, okay? But suppose I start with the BD and I first mix to a BD bar, and that decays to the same final state. So that would be path two, to go first from BD to BD bar, and then have the BD bar decay to the final state. Okay. Then what can happen is you can look at the interference between paths 1 and 2, and that's going to give you a handle on CP violation. So that was a prime goal of the B factories, was to observe this type of B decays such that we can get a handle on certain Cpa symmetries. Now, don't get me wrong, that's not all they measured. There's lots and lots of things they can measure, okay? But this is one of the hallmarks. And in particular, the Cpa symmetry for B to psi, J psi, so that's charmonium, okay? K short, like so. J psi is a CC bar, okay? So in other words, this would be a B to C transition, okay? And so this object is related to the angle beta of the unitary triangle. Okay. And before the B factories, it wasn't clear basically whether the CKM picture of CP violation was really what's dominating. We saw small effects in the kaons, but those could be, and remember, it's not because the phase was small, it's because there's small mixing angles there. But it wasn't clear if that was the picture or whether there was some other, maybe there was some other sort, other theory. We just didn't know. There was not enough, the theoretical uncertainties in that system were just too high to make a definitive statement. But in the B system, partly because the B is a heavier quark, we have sort of different handles on handling the hadronic uncertainties there. And because what's going to be related here is that basically the Cpa symmetry of this B to J psi K short is related to sine 2 beta, and it turns out to be order 1. It's basically predicted to be about 0.7 in the standard model. And so this thing was first measured in 2001 by the B factories, Babar and Bell. And of course, with any CP asymmetry measurement, these are not such easy things. So there's big error bar at first. I remember as a postdoc, people were excited. You think, oh, maybe there's other sources of CP violation. Maybe the CKM phase is actually small. Maybe it's even 0 perhaps, although there's no symmetry reason for it to be 0, but maybe it's tiny. Maybe it's not what's telling us what's happening in the cans. Maybe it's something else. But if it was something else from new physics, you'd have to work pretty hard to understand how this tree level process, remember B to C transitions are tree level. So how this tree level process could somehow be mocked up by new physics in some, which often comes in a loop or has very strong constraints on it, okay? So this was measured in 2001 and the dust settled. a few years later, and this is one of the places where, as it's happened in many sectors so far, the standard model reigned triumphant, and indeed this beta angle through this process was measured and interpreted and completely consistent with the standard models. So if we go back to, let me try to draw the unitary triangle again. I feel like I'm tempting fate every time I try to do this. Okay, rho bar, eta bar. So we have a triangle like so. Remember, it's this angle here, that's the beta, right? We had some kind of circular constraints from VUB, like so. And what this measurement, into beta at the B factories, it's going to tell us some particular range of the beta. So if I try to draw it, we're going to get basically like a little sliver of possible values. And you see they've all got to overlap, right, into this point. Remember, this is that rho bar, eta bar point that we're trying to determine to tell us what the values of these things actually are. Of course, in reality, it's more complicated. There's, you know, multiple solutions when you try to interpret what the beta is from the sine 2 beta, et cetera. So this is really a cartoon version. But ultimately, if you go and you look, for example, here's the two sets of CKM fitters. There's UT fit and CKM fitter collaborations, and you can go look on their websites where they have absolutely beautiful pictures of the unitary triangle with all the different constraints. So by the way, the epsilon parameter in the kaon system is also going to put some constraint. It's a very complicated one, some hyperbola sort of thing, which also would need to overlap. And there's many other data now since those experiments turned on. Okay, so this is the level of where I'd like to, let's see, I think we're getting close to time. Is that right, Heather? I'm just trying to figure out how to kind of end things up in a sort of nice, quick way. Let me, maybe I'll just comment, because I'm here with it right now, is that let's just comment, for example, using the same kind of argument as before. To get the CP violation, what really needs to happen is you need to do interference not only between a tree and also a penguin type of diagram. So penguin is our John Ellis sanction word for loop diagrams. Okay, so like so. So suppose I have, here's a D and a B, and we're going to have a W here. That's the tree amplitude. Okay, so we also could have things like this, just even in the standard model, right? Like so, again, D and B, okay, like so. And so these penguin contributions, and these could be any gauge boson of the standard model. Notice we're not flavor changing here any further than what we wanted to do here. We want to compare these two objects. So this is the tree, and this is the penguin. So if we write down the amplitude, maybe I'll do it right here. If I write A psi k, there's going to be a VCB star VCS, a tree level part. We call it tree, okay? And then there's also going to be the loop part, where again, now we're going to have a sum over internal U-type quarks, for example, in the loop, if this is a W, then we're going to have VQB star VQS, and then there's going to be some penguin. This is the tree psi k, and this is going to be the penguin psi k. Okay, and you can use this same type of unitarity trick that we did before to rewrite this thing as a VCB star VCS. Let me just call it T psi k, capital T, plus a VUB star VUS, E psi ku. Okay, and so this thing includes the tree part plus some penguin contributions, just as we had before, right? We're going to subtract off certain combinations, and this one is just going to be a pure penguin part. So what's important here is that in this particular decay to measure sine 2 beta, it turns out the tree amplitude is it's very dominant, and so what happens there is that it's going to be much easier to extract the sine 2 beta out, the weak phase that we care about, this beta angle. Whereas when we have the loops involving other things, it turns out to bring in new hadronic uncertainties. If extremely important, then what would happen, it would be very, very difficult, even given the measurement, to try to get a precise constraint on the angle beta from the measurement of the Cpa symmetry in that B decay process. Okay, but this was called the golden mode because it was known that the tree was going to be the most important one. It's going to be theoretically very clean, and in fact, it was measured right away. The other CKM angles, alpha and gamma, both suffer from what this contribution where the penguin part comes in and is non-trivial, meaning you can't just drop it because it's subleading. Those are what are called penguin pollution, rather dramatic term. So the penguins pollute the system, and so that pollution hinders the extraction of the alpha and gamma with the same set of E's, and so it's a very, very active set of research activity is to try to minimize that and find ways to get handles on the alpha and the gamma. Okay. All right, so let me just sort of conclude this current discussion just by saying that, okay, so far, I just talked a little bit about the B factories and what they sort of first did to test the CCAM picture. Overall, the CCAM picture is looking very robust, but as I'll start with next time, there are now a couple of ambiguities and anomalies, I should say, in certain B decays that have been seen, and some of them were seen even at these early B factories, the Bar and Bell back in the late 2000s, et cetera, and some of them also seen recently and more by Lhcb. So that's going to give us some interesting handle on what new physics might be, if it's new physics, as opposed to other sources of possible uncertainties. Okay, so that will be for next time, if I've got the time right. Am I right, Heather, that I'm kind of almost out of time?
I think we should probably wrap up. There are a couple
more
wrap up questions.
Here. That's okay.
Yeah.
Good.
One of them is how to test whether the triangle is closed or not.
Oh yeah, that's part of the precision aspect, absolutely. So ultimately, that's what you want to do. You want to see, is the thing closed? And to really be able to see that, you've got to pin that thing down. Okay. And indeed,
I think it's that if you have multiple different experiments that tell you where that top vertex of the triangle is, and if they don't give consistent results, then you know something is wrong.
Absolutely, that's exactly it.
Yeah. And the other question is coming back to that Hamiltonian. I think the point was not gotten.
Oh yeah, this one.
Yeah. So I think what's going there is you're annihilating a K bar, so you need to annihilate a D bar and annihilate an S, and that's the first D bar S, and then you need to create an S bar and create a D, and that's the second D bar S.
That's right. Yeah, it is the kind of operator that when you're first looking at it, you're like, oh, it's a typo, and then you're like, then you look more carefully, and you're like, no, it's not.
Yeah, the delta S equals 2 is a clue, right? Because you're getting rid of 2D. Yeah, you're annihilating 2 S quarks.
That's right, 2 S quarks. That's important.
Yeah. Any other questions? Okay, I'm gonna give people time to type. I should also ask, do the students have any announcements that you want to make about talks or things like that? If so, we can unmute one of you, I think. I can't, but people can. Okay, I'm not seeing any hands. Great, I guess that's it from the lectures for today. Just a couple of quick announcements. I put a post in the Slack in the general